Welcome to part 2 of the Hitec Telemetry series, where we'll discuss installation best practices for each of the sensors and the sensor stations. Let's get started. The HTS temperature sensor comes in a 2-pack and is probably the most versatile temperature sensor or versatile sensor that they offer in the Hitec Telemetry suite. The reason being is you can use it for so many different applications, from monitoring the temperature of the motor, the battery, the exhaust air coming out of the fuselage itself, speed control, external BEC, the list just goes on and on. Again, it comes in 2 pieces, or 2-pack, so these are 2 identical sensors. The temperature sensing range is minus 40 degrees Fahrenheit to 392 degrees Fahrenheit, so it's going to cover just anything that's going on within your aircraft. But if you do want to temperature sense the actual fuel motor, like if you have a gas motor or a glow motor, you're better to look at the HTS engine sensor, which is the same core sensor, but it's encapsulated in a metal bullet, and it has a couple mounting options for you to be able to affix it to the motor itself. This shrink tubing is not really meant for that type of application, so you're going to want to take a look at that specialized sensor for fuel applications. But connection is really simple. We've got it connected through our HTS iView, which is running into our iPad, so we can see the real-time. In fact, right there, the temperature line shows -40. That's the low-end range. It just registers -40 when you don't have anything plugged in. But you can plug these in real-time. It won't hurt a thing. And we'll go ahead and plug it into the T. You have T1 through T4 on this particular sensor, which is the HTS Nitro, or HTS SS Nitro. I'll plug it in, and as soon as I do, you'll see that it registers now the actual temperature range of 79 degrees Fahrenheit. It's very fast responding, has about a 1-second pole interval through the HTS iView. So as I put my finger on there and it starts reacting to my body temperature, you'll see the temperature climb up. So it's very responsive, and again, great way to monitor different applications. For example, I have a large cell battery, a 6S battery here. The thing that's nice is you can pretty much put these anywhere. You can use everything from you know, a Velcro tie wrap. If you're putting the motors down, the batteries down, you can slide this sensor underneath it as long as it's making good contact. Now the actual sensing part is up at the very tip. You can see the kind of barrel at the very tip of it. You're going to want to put that up against the battery and just make sure that's making contact with it. The thing I like about these larger cell batteries too is there's usually a little bit of space under the shrink tubing, like in this battery's case. I can just slip it underneath there. There's no pressure at all on the cell. It's not like it's pinching anything. And now I've got really good contact down to the foil pack underneath, so I get very fast response temperature readings from my battery. So you can, if you have 2 batteries going on, you can just plug in a second sensor. Again, you can just plug these right in easily. So even if you forget to add them in and you've already powered the model or whatever and you need to plug them in, that's fine. Now we see our second temperature sensor is registering ambient temperatures again, and I can hold my finger on there and we'll see it climb right up. So if I get a second pack, I can slide a second pack sensor in there. Again, a very versatile sensor to use. Brushless outrunners, for example. Now the stator rotates around the motor itself. It's part of the barrel of the casing. So of course we can't put anything from here forward, but we can look at the back end of the motor and usually have exhaust ports, and those are non-moving parts. You can see on the camera that there's nothing moving visibly in the back end of that mounting plate. So I can just insert that in there. This is insulated. It has heat shrink or shrink tubing around it. Put it in there until it makes contact, and then affix it in place with some tape or even epoxy. If I wanted to make this a more permanent connection, I could put a little bit of epoxy right there on the motor mount itself and encapsulate those wires, and it'll hold it in place. We see a larger motor example where, again, you have to get kind of creative sometimes depending on the configuration, but you can apply the temperature sensor anywhere where you're going to get good airflow or good contact with the motor. Contact, of course, is the best for any moving parts that you've got. You can bend the wires. Again, kind of stay away from the sensor head itself, but you can bend the wires if you need to for specific installations to be able to hook around and then mount the wires to the back of something. So installations are flexible. We've also put them on BECs. You can see here where it slipped down between the heatsink fins very easily, and all we did was press the 2 fins together just slightly, and it actually grabbed onto the sensor really well and gives us fantastic readings from our external BEC. On this little motor we see we've got an external heatsink again. I would mount it inside of there, making good contact with the heatsink, and I could always use a little bit of epoxy on the back side if I wanted to make sure that that was held in place and always had good contact. Now, if this in-runner didn't have the heatsink applied to it, I could just take the sensor and put it right up against the motor body itself, or the motor housing, and hold it in place. Now, you got to be mindful, you don't want to wrap this in Velcro or tape, because then it can actually act as an insulator and take away some of the cooling of just the body hitting the moving air. But use your imagination, and you can hold the wires down, and there's enough spring tension and the leads going to the sensor itself that will make good contact with the motor. So depending on your installation, there's a lot of different ways you can use the HTS temp. Building off the HTS temp sensor is the HTS engine temp sensor. Again, the same specs, minus 40 to 392 degrees Fahrenheit for an operating range. There's a little different layout though. What you'll notice is they use a little stiffer wire, a little more temperature resistant wire. They also have a pretty significant heat shrink tube lead from the sensor itself to be able to insulate the wire against the engine casing and other hot parts. You're going to want to try to keep that as free from contact as possible regardless, but this does give you some additional protection. But then the sensor itself has this metal barrel that the sensor is infused in, so you get much better contact, conductive contact between the engine itself into the sensor. So it's really what it's designed for. In fact, they include a couple of different brackets. You just slip the sensor into the end of the bracket itself. Crimp this down gently. You don't want to crush the sensor, but just crimp it down to where you don't have any free movement. It feels like it's fixed in there pretty well. And then you have the benefit of mounting this directly to the engine block. For example, here's a 55cc engine. A lot of different options for mounting here. I could go off of the head itself. I pull the bolt back and slip that underneath the head bolt itself and crank it down. I've got engine casing bolts. And then of course the mounts themselves, the engine mounts. I can certainly sandwich this inside the engine mount and mount the engine, and that would give me good sensing as well. So the goal being is you have direct conductive temperature sensing from the engine itself through this bracket and into the sensing head. So really good and ideal for fuel installations is the HTS engine. You do not want to use the regular HTS temp engines or temperature sensors in this application because they're just not constructed to be able to handle the heat or also the vibration. This is built for both of those applications. As far as plugging them into the sensor station itself, it's the same thing you do with the standard temperature sensors. You don't need a special port. You just use any of the engine temp or the temperature sensing ports on the sensor station. And if you'll notice, as soon as I plug it in, it begins to register 73 degrees, and you'll see it increase quickly as I hold on to it and conduct my body heat through that temperature probe. So that's it. Same installation as the HTS temp sensors, but specifically built for nitro and or glow and gas motors. Go ahead and finish out the sensors that are exclusive to the HTS SS for nitro sensor station, and of course the HTS fuel is one of those sensors. This is a fuel level sensor that utilizes external pads, sensor pads. These are double-sided adhesives, so you can stick them in different orientations. The pads do have 4 sensors each in them, going along the length of the sensor pad itself. So empty to full. Now this can be in the opposite orientation. The sensor is intelligent enough to understand this is the first one to show fuel, so this becomes empty to full. But the key is you don't want it sideways in the tank. Like I have it right now for this demonstration. I'm going to have it in vertical orientation. Normally we would have our tank sideways like it should be in our airplane, and we would mount the pad this way or this way, and same with the smaller one. So the key is to pick the pad that fits the tank properly. You don't want to be too large because it's going to give you some false readings, or you're going to find that you go from full to 3/4 pretty quick. I would find the pad that fits the tank most effectively, which this one in this case would be about the right size. This one would be a little bit on the large side, and keep in mind if you're going to err to the safe side and shift the pad up. If this is lower orientation or bottom orientation of the tank, shift the pad up a little bit from empty to full. That way you've got a little more fudge factor. If you do run low on fuel, you know that even though it's showing you empty, you've got a little bit of emergency to come in if you're using a smaller pad. Ideally you want a pad that fits about the right size of the tank. And this is, again, pretty darn close. It would work just fine, and I would go ahead and position it right about there with a little bit of extra room on the bottom, so I know, again, I'm giving myself a little more, maybe 2 more passes at half throttle or lower throttle to be able to come in and do a land if I have to do a wave off one time. So that's all it is. Stick the sensor to the tank itself, and then you've got 2 outputs on each one of the sensor pads. The white arrow indicates the orientation that needs to be plugged into the HTSS fuel. The little brass contacts are sticking up on this sensor, so we want to insert it this way, and all you do is get it lined up with the slot, hold it kind of close or pinch it kind of close and push it in, and you'll be able to get good contact. And there it is. The sensor is plugged into the pad itself. Now they do include a little piece of double-sided sticky tape as well for the sensor pad or the sensor itself. You can stick that on there to adhere it. It can be stuck to the side of the fuel tank, or whatever makes the most sense for your installation. It's not going to hurt a thing. So we've got a sensor pad stuck in here for demonstration purposes. Now keep in mind, these sensors pads will only read glow fuel at this time. They won't do gasoline, so this is applicable for glow fuel applications only. Ironically, it will read water, will sense water, so we're going to use water in our example. And you can use water to test as well. Just make sure you let water out of your tank before you try to fire up your motor. but we're going to use water to show that how it registers the different fuel levels. So plug in your sensor to the sensor station, and it goes into the F port, F for fuel, and you got a 50% chance of getting it right, and I usually get it wrong. There we go. It's keyed, so it'll only go in one way. Our sensor's in the sensor station itself, and now we're going to need to plug in our fuel sensor pad to the sensor station. And again, all I'm going to do is pinch that kind of close to the arrow, and then insert it into the sensor. There we go. So our sensor is mounted. Now, of course, what our operations are: turn on our transmitter first, and tell it okay to transmit. And what I'm going to do is go ahead and power on the receiver, and then we'll do the HTS view as well. So now that the receiver's powered up, the transmitter understands that there's telemetry connected to it, so we can go in here and choose sensor and cockpit, which is kind of nice. It just gives us all our different sensors that are connected, and we'll be able to monitor our fuel level then as well off of the Aurora 9's cockpit view. And then we'll go ahead and power on the iPad. We'll launch HTS iView software. And again, this is just optional. For demonstration purposes, it's easier to see the display on this than it is on anything else. So, and then it does show the fuel indication right there, a little gas pump. We can go into detail, fuel, and it'll also show a larger view of that as well. So now we're ready to go ahead and start adding in some water and seeing how it registers the what would be our fuel going into the tank. And there's quarter tank. There's half tank. And it's coming up on the 3/4 sensor. There's 3/4. And there's full. So it's it's very fast reacting, and of course we have that view. Go back over here to cockpit. We have that view on our Aurora 9 as well, so there's our gas tank full. Now if I tilt this, we can kind of fool the sensor to thinking it's losing fuel. And there it's down to 3/4. You can see it reacts instantaneously to the change in the level on both the Aurora 9 and also on the, there we go, there's a quarter tank, and then we'll go ahead and there it's empty. So we got it back in, and there it is. It's a very simple sensor to set up. It's very easy and flexible for different tank configurations, and it's really simple. It's kind of a no-brainer. There's not much to take into consideration. It works great in multiple environments, and it's very reliable. So that's the HTS fuel level sensor. Okay, now applicable to all three sensors stations is the HTS GPS sensor, and this is definitely the fun one. This is kind of the flash and fun sensor of all the telemetry sensors. If you just get into stuff that's interesting information, I guess I'll put it that way. The HTS GPS sensor, it's a multi-axis GPS sensor. See, it's very small and compact. It does connect to all three sensor stations. I just moved over to the HTS SS Advanced. I grabbed that since I went ahead and took the HTS SS Nitro and stuck it out on the hood of my truck, so it's getting information back to the system. It's very simple to connect. You know, outside of the standard data connection and power connection that's required by any of the sensor stations, you just simply find the G port and you plug it into the G port. Now, one thing to keep in mind is with the GPS, there's a few things to consider and remember. When you move to it, and that's it, it gets its power through the power port, the power it's supplied to the sensor station, and then the data connects through. You don't have to have any other sensors plugged in to use the GPS. It functions all on its own. But one thing to keep in mind is when you power on the receiver and you move your GPS sensor, your aircraft, to a new location, it can take up to 5, maybe even 8 minutes to register, to get enough satellite fixes to be able to register its exact location. And you'll see on the display I have up, the GPS mode display up on the Aurora 9, this is what it's reading from outside. It sees, you know, my absolute latitude and longitude position, the altitude 842, 840. It's going to fluctuate between a few feet, but that's right on the money for my current location's altitude above sea level. And then of course it will register speed as well, the forward speed. Now one of the neat things too is you'll notice as you go to the HTS iView, if we look at the cockpit view, it's going to give us our altitude. Pretty limited stuff here inside the Aurora 9, just because there's so much to display. The easy view, Again, we can go to multiple pages. There's our speed and our altitude shown really large with max, and again, that's like any other GPS. If you use your regular vehicle GPS and you leave it on all the time, it's going to get some false readings on speed and even some of the other positioning, latitude or longitude positioning. So this is our, our current 849, fluctuating around feet above sea level. And we continue down through there, we can see the other views within the cockpit view, but we do have a display that shows us our large view. What I like about the HTSI view, and also the HTS Navi, which is the USB interface that you can use on their telemetry system as well, which gives you a PC reading, is it does give you distance from yourself to the model and the radio distance, and it also gives you the altitude of the plane. And you can do that a couple different ways. In fact, you can go through, if I go to my GPS view, I can look at altitude. I can go to setting and I can say altitude absolute or relative. So if I go relative and I go back to my GPS reading, my altitude is at 0 feet. It's the height in which, the altitude in which I started off, in which I initialized the GPS. It's at 0 feet, so it'll register how many feet up my plane continues to go in altitude. That's the way the HTSI view is by default. You can't, as far as I'm aware, you can't go into set the relative or absolute. It's always going to go absolute. So since I'm in the existing location where I started and I initialized the system, it's going to give me that information. Speed, of course, does register, and that's always real time. In fact, on the main display, you will see your speed registered as well. One of the main ones, the main dial is most visible. So very flexible as far as installation goes. You'll see in this particular example, we've got it located underneath the fiberglass cowl on a 3D airplane, and had no problems whatsoever receiving information. It worked flawlessly, very consistently. We've also tucked it up underneath the foam canopy of like the multiplex dogfighter. That's great because you just kind of hollow out a section of the canopy, kind of auger it out to fit the shape of the GPS sensor. You shove it up in there and it friction fits really well inside of the canopy and gets fantastic signal through the foam, and it's up out of the way. So it doesn't really seem to have any problems. We've tested it in multiple scenarios, as well as the Hitec engineers have tested it around different types of interference, so you don't have to really worry too much about placement. I've had it located close to BECs. I've had it located relatively close to speed controls, and no problems whatsoever. It worked absolutely flawless. It's a very flexible, very simple to install, and fun sensor for the telemetry sensor suite. Moving on to the RPM sensors, there's two RPM sensors available. There's the HTS MRPM and the HTS ORPM. This is the magnetic RPM sensor, which is what you're going to get the highest level of accuracy off of it, but it's also going to require a little more time and effort in installation. So what the package includes is the sensor itself, and then you also have a couple of mounting screws, because there's two mounting holes in the bracket for the sensor. And then also a few rare earth magnets. Here's two of them right here. They usually include 3 in the kit. And then the rare earth magnets are what you're going to attach to your motor or whatever rotating part you want to track. When you look at them closely, you're going to see that they have a little tiny X on them. What you're going to do is have the X facing towards the sensor, the actual sensor itself. So in this particular example, I'll show you, we applied or installed the sensor bracket or sensor itself to a bracket we just made out of stiff wire, attached it to the motor mount and pointed the sensor inwards towards the motor, and attached the small rare earth magnet to the stator of the motor, the outside barrel of the brushless motor. And you want to ensure about a max you want is about 1 millimeter clearance. You want to get it pretty close. Keeping in mind vibration stuff may actually cause contact. You don't need it to be completely almost making contact. You want to have a little bit of distance there. But to get the most effective readings, you want to stay within about 1 millimeter distance from that sensor and the magnet itself. So if we try to take that example we did earlier down to something more practical, like this small little tiny outrunner, all I'm going to do is pick a spot on the barrel of the motor itself and attach the magnet. Now I've got the X facing outward. What you typically do is rough up the barrel itself. You can take a little bit of sandpaper, you can take a small sanding wheel and clear off some of the paint. And then also it's good to rough up the magnet on the other side, is to create a little bit of texture on it. So if you can, get a hold of some pair of pliers and just kind of rough it up a little bit on some sandpaper or your small sanding wheel. And then you want to use either medium CA, which we found works pretty well. Just give it plenty of time to cure. or you can use a little dot of epoxy, two-part epoxy, mix it up, and just put a little tiny dot on there and then stick the magnet over top of that dot, so you've got two good raw metal surfaces making contact to get good adhesion. And we've spun these things up and haven't lost a magnet yet using that method. So, but there it is. I mean, it'll for testing, it's nice. It'll stay in place for you on the barrel of the motor, so you can spin it around and test your connection. But it's really simple. You got the sensor itself. Again, the easiest way is to get some stiff wire, some heavy gauge wire, and bend it into a bracket that fits your application. It only takes a couple of minutes with a pair of pliers, and you can get it just about perfect. And then use your two bolts and nuts. You may need some washers to be able to grab that wire well and not allow it to flex around. But mount that bracket then to the wire bracket that you've made, or the actual sensor to the bracket you've made, and then you're going to get it pointing towards the barrel of the motor. And we have it, we'll go ahead and connect it. All there is a single connection. This is supported on multiple sensor stations, the Nitro, the SS Blue for electrics, and also the SS Advanced. And you've got 2 RPM slots on this Nitro, R1 and R2. It doesn't matter which one you plug it into. It's just a RPM sensor, so it's going to show up as one or the other. And depending on what you're connecting it to, like in the case of the Aurora 9, I can rename this to be able to identify, you know, motor RPM or gear RPM or gearbox RPM or whatever I want to call the particular sensor I have or sensors I have plugged in. So now that it's connected, what we can do is see both on our HTSI view and also on our Aurora 9 that we have the ability to kind of fake it. We'll just pass this over top the magnet, and there it goes. It's registering some speed. Now it's going to be real erratic because I'm not consistently holding it any specific distance, and I'm just moving it back and forth. But you see it's registering, you know, 280 RPM. And it's pretty darn accurate. We've had some really good success in a varying range of motor speeds up into the, you know, it registers 5 places, so you can get into the tens of thousands of RPM from really high spinning, high kV motors down to the larger ones like you saw in the example. Very accurate results, and a great way to identify what you're actually getting out of your prop. If you do your calculations off your motor kV and you size your prop based off the kV, it's always nice to know the real world without having to use an external optical RPM sensor like a handheld unit that we see so commonly used. This will give you a really nice accurate reading, and it's built into the aircraft, so as you make prop adjustments you can just glance down at your transmitter right out in the field and see what you're getting out of the engine, or the motor. So it's a nice way to keep those field diagnostics going. But that's it, and as you can see, it'll still pick up as I get a little ways away. It's still registering, so even though it needs to be pretty close, that 1 millimeter distance, you'll find that it's pretty forgiving. If you get a little bit outside of that, it'll still function just fine. But that's it. It's a really simple sensor to use. Once it's up and going, it's really consistent performing. It's just going to take a few minutes to get the thing installed, and you want to take your time and make sure you've got your alignment good. You're not getting any sort of physical contact. Keep in mind, as things get vibrating in the air, you don't want to be so close that you're almost making contact, because then there's a higher probability that that vibration will allow it for the magnet to make contact with that sensor, and I guarantee you won't be happy with the results. It'll shatter that sensor very quickly, so you'll have a broken sensor if that glued-on magnet makes contact with it. So just keep that in mind. Otherwise, it's a very simple, straightforward installation, and it works extremely well. Okay, the next sensor is the HTS ORPM. It's the second RPM sensor. This one's an optical RPM sensor, and it's really designed for helicopter applications. It comes with a small module, small sensor, optical sensor here. You can see with a cord that connects to the sensor station. It also includes some double-sided foam sticky tape to be able to help mount it, secure it on the boom itself, and then also a couple of tie wrap fasteners to be able to really hold it down. They do optionally give you a couple of screws, so if you're surface mounting it on something, they do have a couple of small holes in there as well, as you can see, that would allow you to screw it into, to fasten it into something. But again, it's really intended for helicopter tail booms. With this is, this is a small carbon fiber boom, and what we would do is just mount it. It already has a round in the bracket, a little bit of curvature in the bracket to be able to help it cradle over top of a boom, as you can see. It won't spin then too much. It stays in place. And all I do is put my foam tape on there and run my tie wraps around and fasten it down, and it'd be secure. You want to be about about a third or half of the way out on the boom itself, so you're away from the pod or the body of the helicopter, and you've got good clear view between the sensor itself and the rotor blades as they pass. And that's all it is, an optical RPM sensor, so it looks for interruption in light. It's just like the optical RPM sensors we would use externally. On a helicopter, it's kind of difficult to get up close to those things while they're running and try to hold your optical RPM sensor or your handheld to verify that what your governor and your gear ratio is stating as your head speed to be is actually what you're getting. So this is kind of nice. It's permanently affixed inside the aircraft, and at any given time, you can check or verify that your RPM is where it needs to be. Now, keep in mind, as you get going through different maneuvers and the light changes, you're not going to get highly accurate readings out of this. It is really optimized for that RPM range of like a helicopter head, 2,000, maybe 22, or even as high as 25. Some insane guys take it up, 2,600 on some of the really hardcore, high-performance helicopters. But they're below 3,000 RPM. As you get props spinning up higher than that and stuff, it's just going to be difficult for the sensor to do a great job, especially in changing light conditions. So we have, in this example, mounted it on a fixed-wing aircraft. And we've got generally pretty good readings if we're sitting stationary and we're just doing static testing of different props to see what kind of engine RPMs we're getting. But again, once we start moving around and the light starts changing coming into the sensor, it gets less and less accurate. But once we return back down to the ground, it does a pretty good job again. So just simply take the connector end, plug it into the sensor station. In either one, this Nitro sensor station has R1 and R2. Either one will register just fine. I'll go ahead and stick it in R2 just because it's closer. But the nice thing is, with a lot of these sensors, you can do bench testing without having to power down and repower up the system. It'll just start reading the sensor right away. Now we're under microfluorescent lights here, so compact fluorescence. So we're going to get some really erratic readings. Light sensors work best with an analog, light wave coming into the sensor itself. So outdoor lighting is much more effective when it comes to light interruption. Since this is on a pulsing frequency, it tends to mess with or interfere with the optical RPM sensors quite a bit. In fact, as you see, I just move it around. Sometimes it'll jump a reading. But out in analog lighting conditions or standard lighting conditions, even incandescence as well, that's an analog light form, light source. So it'll be much more consistent results. But we can go ahead and wave our hand over here and see if we can get a little bit of, there we go, some RPM registering from the optical RPM sensor. So really straightforward, mounted to the tail boom of the helicopter, pointing up at the rotor blades. Make sure it's secured, fastened really well with the included fasteners, and that's it. It's an easy way to do some field checking of your RPM. We have had success mounting these behind props if we were out away from the spinner enough to be able to get some good light interruption. Relatively inconsistent results during flight, but on the ground it worked out pretty well for sizing out props and getting some RPM readings off our motor. We're going to cover both of the current sensors in one shot here, the HTS C200 and the HTS C50. Now the C50, these are both induction current rings is what they are, sensors. As the main battery leads are passed through this inductive sensor, it picks up the current that's passing through the cable during operation. So it's ideal for electric power plants, and you want to tap these into the main feed from the main flight battery. The 50 will go up to 50 amps, and then the C200, a little less resolution, but then it'll go up to 200 amps in sensing. So real simple connection. It's a single, just like the rest of the sensors, a single wire connection, and you're going to look for the C port. In this case, it says C and V on the HTS SS Advantage. That's current sensor and volt sensor. So all we're going to do is to show you how these are typically installed. In this particular example, we'll show we went ahead and mounted the HTS C200 on this power plant because it was a larger application, and it drew over 100 amps in current. Just passing it through, one of the formers and the bulkheads in the airframe, and then passing the wire through it, we were allowed to get able to get a good location, a good fix on the wire, and also a nice stable location. And we just passed the positive lead through the induction sensor, and got really good results with that. So we'll show kind of a bench example here as well. Now normally what you do is again, you're going to want to catch the current coming from the main flight battery. So in this case, we have our incoming lead from our flight battery. Before we solder on our connector, what we would do is pass this sensor, the current sensor, onto the positive lead. And you want to make sure that it's going in the direction, you see there's an arrow on it. You want to make sure it's heading in the direction of the current flow. So if we were monitoring, we could monitor the negative and have it shoot back towards the battery, or we could monitor the positive and have it go towards the ESC. You want to catch the direction in which the current's flowing. So that's what the arrow is for. So make sure you have it oriented properly when you install it. In the example we're going to use, we've just got a flight battery here, and we've got it hooked up to a charger-discharger. So we're going to go ahead and start a discharge process, but the reason I chose this is because I can just simply take the HTS C50 and pass it through the charger lead. So we'll have it mounted on the battery leads coming from the battery, and it's in the direction flow. In this case, I actually got it backwards. We want the flow towards the charger, like we normally would if we were installing it to an ESC. So we'll use the discharger like an ESC. We'll start a discharge process, and there we go. Our arrow's heading in the right direction. And then all we do is plug that into the sensor station, into the C port. And once that's plugged in, we can see on our HTSI view, here's our current listed. Now, it doesn't matter which one you sent, which sensor you plug in. It's all going to go into the current port, and the system will automatically adjust for whatever it'll handle based on C200 versus C50. It's really more about the ring as opposed to, you know, the port you're using or the ability of the HTSI view software or the Aurora 9 or your other telemetry radio systems to detect what's going on. So now that we have it in line, it's not uncommon to get a little bit of transient voltage coming through, amperage coming through now. 0.2 is what it's reading. We'll go ahead and start this discharge process. And let's check in the battery, and there it goes. It's now discharging. And we see it as the charger ramps up its discharge current. We'll see the inductive coil or sensor also registering the current that's passing through the line. So I've got this set about 1.8 amps, so it's going to bounce around there on this discharge. And you see it's pretty darn accurate. I've got 1.78, 1.8 amps registering on my discharge, and it's rounding up on the HTSI view. About 1.7 consistent. There's 1.8 coming from the battery now to the discharger. So it's that simple. It's really about remembering that you have to put this inductive sensor, this ring, in the line before you permanently affix everything. And once you get your leads on, of course, if, like in this case we're using EC5 connectors, very difficult to get the connector back out. In fact, it's ruined. So if you have to disassemble and reconnect, you've ruined the connector. So you want to think about that during the build process, and run a little test to make sure you've got it going in the right direction. If you're unfamiliar, if that doesn't make sense to you to catch the flow of the current. But it's also important to keep that wire centered as well as possible inside the inductive ring. You'll get the best accuracy if you keep that wire centered. So in this case, you know, it's not too far off from center even when it's off to the side, so we're getting pretty good readings on it. But especially as you get up to like the C200 sensor, it's a much bigger ring, and even though a 12-gauge wire is pretty thick, it's still going to slop around in there pretty well. So what's pretty common is use either like hobby foam that you would use under a fuel tank or to isolate the receiver. I've even used a little piece of silicone fuel tubing and split it and slip it over top of the wire to where it keeps it centered nicely inside of the inducting ring or inductance ring, so you get the most accurate reading since this is working off of that magnetic field. So, and that's it. They're really straightforward. They're easy, easy to display in both the HTSI view, and of course it's going to be visible within your Aurora 9 display. If we go to System and go to Sensor, we've got our Easy View. There's our current registering 1.9 amp. Now one of the neat things too, and we'll talk about this later, it's kind of cool if you do the voltage sensor and the current sensor, it will calculate wattage real time too, so you can see your real-time wattage consumption. And also, since you can store this information through either the HTS Navi through the PC or through the iView software, you can always recall what was taking place throughout your flight at the end of the flight time. So current sensor is very simple to install, very easy. You just have to follow a couple simple directions and make sure you have the right sensor for the right application. If you're getting close to the 50 amp, there's no crime in using the 200 amp sensor. Just realize you're going to have a little less resolution, so it's going to go in 1 amp increments with the 200 and not give you quite as fine a details as the 1/10 of an amp that the C50 will give you. But if you go over the 50 amp, it's not going to be able to sense it anyway, so make sure you've got the right sensor hooked up to the power plant. And you can really gauge that based on your ESC. For example, if your ESC is set up, your entire power system is relying on a 25 amp ESC like this one, this 25 amp ESC, the most it's going to consume is 25 amps at peak. Even in fault conditions, you're still going to be around 25, so we could very comfortably use the C50 sensor in this power plant setup. The HTS volt sensor picks up where the SPC port built into the Optima 7 and Optima 9 receivers, for example, leave off. The SPC port can measure up to about 35 volts max. As you go into larger or higher voltage applications, you're going to want to actually use the volt sensor, and that's good up to 100 volts DC. So the HTSS Advanced and also the HTSS Blue for electrics has the voltage sensor capability in the sensor station. So you'll need one of those two to be able to take advantage of the HTS volt sensor. It looks a little confusing when it comes out of the package. You've got, just all it is a wire lead, both positive going into the connector, and then this little chunk of, looks like about 16 gauge wire. And then you also have a little alligator clip with the same kind of connector. This just gives you two different options for connecting in the volt sensor. So on a typical electric power plant, we'll resurrect our old test DSC again. You've got the actual battery leads coming in. Now, in the SBC clinic, we talked about how to connect these. We left it bare so you could see how to pigtail that into the main pack leads. But what you have is you want to tap into that main pack voltage, and that's the reason for the volt sensor. Is you're now sensing that main pack voltage coming off your flight pack, so you can monitor that within your actual telemetry software, either on the radio and set up monitoring and alerts on your HTS voice module, or on your HTS iView on your iPad or iPhone software, whatever makes most sense for you. But the goal is we're monitoring voltage at higher than up to 100 volts. You can use the voltage all the way down to a single volt. It'll do everything the SBC port will in terms of detecting the lower voltages, but it'll allow you to go much higher, up into 100 volts. So the goal, or the reason these little connectors are available, is because they don't really know the application you're going to use it in or how you're going to tap into that main pack feed. So for example, we may want to actually tap into this line without soldering. So this would be one solution, is using the included clamp. This is just an inline wire clamp. You would slip this lead into the one end, compress it down, and it's going to stab a couple of little contacts into the wire to tap into the wire. And then you do the same thing across these main leads on your ESC. Is you would open up this little clip, you would slip the main lead in there, the positive lead in, and you would clamp that down nice and tight until it clicks, and there's a real positive fastening that goes on, so you know you've got it in there securely. All you're doing is tapping in. It's just a wire tap, tapping into that main positive lead coming from the flight battery to your ESC. So another way to do it too is to actually solder in a pigtail off of your main pack leads, kind of like what we did here. This one's for the SBC port, so it has a radio connection on it, but it could very easily have like a small micro Deans or something like that. And then what you would do is just hook the positive lead. You would use this wire to solder onto the other half of a micro Deans, and you'd be able to disconnect it then. So if you want to use your sensing system or this sensor, the voltage sense wires in a different application, you can without having to desolder anything. But that's all you're doing, is just tapping off that main lead. So let's take a look at how it connects. We'll go ahead and use the CSC as an example, and how it impacts the sensing within your radio system. So using a standard connection, we're going to go ahead and plug our ESC into channel 3, which is a throttle channel. And then we've got our radio connected, like we typically would. We have a radio connected through our throttle channel. It's going to be fed our power from our BEC, our battery eliminator circuit, built into our ESC. Ignore this lead. This is for the SBC port, which is in the other SBC clinic. And we're going to go ahead and connect a regular battery. I have a 3S 1800 milliamp here. And what we get then is our standard receiver voltage, as we look at it right now, on the Aurora 9, for example, is 5 volts coming in from the BEC, and that's what it's showing here on the receiver battery. Now it'll leave the last state if we go through here and actually exit out of HTS iView. It'll go ahead and refresh that setting then. So we go in, it'll look for the HTS iView module. It says yes, it's connected, okay. And we're going to go ahead and look at the receiver battery 5 volt. So there it is, current voltage. There, just monitor it. It's 5 volts, what's coming in from the BEC. So that's great. We know what's happening there. That also shows up on our Aurora 9. And then the neat thing is about the voltage then, once we plug in the voltage sensor, we're just going to go ahead and use the alligator clip. We're going to kind of do this a little bit renegade here, and I wouldn't advise doing it on your own. Make sure you've got good soldered connections. I'm going to use this alligator clip on the positive lead coming out of the battery, which is going to tap into our main pack lead then, feeding into our ESC. So this is how you actually connect the system. And what this is going to do then is bring this volt setting alive. So not only will we have our receiver voltage, which we know is coming from our BEC, which is consistent, we can also now pick up our main pack voltage, which will register, there we go, 12 volts. So this battery pack is setting at 12 volts right now. Again, this is the same basic function that takes place with the SBC port using this pigtail connection, which just taps off the main leads going to the ESC. But this allows us, again, to go up to 100 volts. So it allows our higher voltage applications, multi-cell setups for helicopters, things like that, or larger cell counts for bigger aircraft applications. But that's it. You just tap it into the line. Now, you're going to use one of these two methods to get into that positive line. How you choose to do it is your own. Again, probably what makes the most sense is pigtail off with the Dean's connector, micro Dean's, and or a small EC3 or something like that. Some connector that allows you to connect and disconnect that. But don't do it on the battery side, of course. It just doesn't make any sense to have pigtails coming off. Always do it on the other side of the connector going to your ESC. But now you have a voltage. Since you have voltage, if we added in current, a neat little thing is if we added in one of our current sensors, for example, this 50 amp current sensor, we tapped it into the main line as well and plugged it in. This would calculate real-time wattage consumption inside of both the Aurora 9 display and inside the HTS iView. We could actually see the current wattage consumption and record all that information as well. So HTS Volt, very simple to connect in concept. You're just going to want to take a couple seconds and think about how you want to do it, how you want to tap into that main feed coming off the main battery, and then it's just a matter of connecting it to your sensor station, and the system's already ready to read the information. The HTS SM is a Hitec servo manager. Now the neat thing, this is for me highly anticipated, just because it's such a question mark when you put together large aircraft and multi-servo setups as to how much current is actually being drawn across the system. So you run into the question, did I size my ESC's BEC correctly? Can I use the BEC? Do I need a 10 amp or a 20 amp external BEC? In most cases, of course, you're always safe going with, like this Life battery. It's 10C, so 1C is 3.2 amps. It's going to deliver 32 amps, no problem, to the radio system. And that's all fine and wonderful, but you've added a lot of weight as well. So can you get by with that smaller external BEC? Well, the neat thing about the servo manager is it allows you to see exactly what your servos are drawing in terms of current. The setup's going to take a couple of minutes here to get you familiar with. It's really simple, though. All you're doing is just adding it in the chain. So let's start off with, we're using the HTSS Advanced. You've got to use the HTSS Advanced sensor station with the servo manager as well as the variometer and the airspeed indicator. So we're going to be using the HTSS Advanced. It has 3 different inputs, M1, M2, and M3, all for the manager. So if each servo manager can handle up to 4 channels, and of course you can Y additional servos or multiple servos off a single channel, you pretty much can cover with 3 available full channels on the advanced sensor station. You've got 12 different discrete channels coming from your radio system that you can monitor the current on. So we're going to go ahead and go through the connections and get you familiar with what it looks like in the radio system. Starting with our Optimus 7, of course, our data channel is going out to the data input on the HTSS Advanced. On the, all I need to do is slave power to it. I'm just, for simplicity and try to keep all the cables going the right way, I'm just slaving power off of channel 6 since I'm not using that. So that'll power up the HTSS Advanced sensor station. You can always take your main power in and Y it off, whatever works best. You're just going to take the radio power and supply it to the advanced sensor station. We're going to go ahead and use HV or high voltage on this, 7.4 volt lithium. The SS Advanced and the sensor stations will handle high voltage no problem. So as long as you give it 4.8, 6.0 or 7.4 HV voltage to both the receiver and the sensor station, you're all set. So we've got those 2 connections. It's going to start getting a little bit messy. I'm going to go ahead and bring in power. I've got a 7.4 volt pack I'm using here for power. We'll plug it into the battery channel on the Optimus 7. So we've got all those plugged in. Now I also need to tap the HTS SM into the sensor station, and then we've got a sensor station connection. I'll just go into M1 since we're not using any others. There we go. And now this is where it goes into the radio itself. So you take the output of the channels on the Optimus 7 in this case, or your Optimus 9 or whatever you're using, and you tie in whatever channel you want to. Now this says channel 1, but it doesn't have to go to channel 1. This says channel 4, it doesn't have to go. These are just channel 1 monitored, the first channel monitored, the second channel monitored, the third channel monitored, and the 4th channel monitored. Because you figure if you've got 3 of these things in a row, they're all going to say 1, 2, 3, and 4 on them. This is just keeping track of 1, 2, 3, and 4 of the channels being monitored. So it can be a little deceiving. You're going to want to use some of your own labeling once you do get this all set up and installed so you can keep track of everything. Let's go ahead and use channel 1 and say that goes to channel 1. That's our ailerons. So we'll connect that into channel 1. And then I'll go to channel 2. But then like channel 3, you know, even on a larger setup, I may not want to monitor that throttle servo. It doesn't really matter to me. I know to be well within my limits. It's really those control surface servos I want to monitor. So we'll go to channel 4 on that. So channel 3 is going to channel 4, and channel 4 is going to channel 5, flaps or something like that. So the point being is you just grab the channels that you want to monitor from the servo manager and run those through the servo manager and plug them in from the receiver to the servo manager. And then on the output side, you're just going to make sure that you're picking up the right one. So channel 1 may not be channel 1. In this case, channel 2 all up to channel 4, or channel 3 is not channel 3, it's actually channel 4. So I'd want to make some labeling to reflect that. But let's go ahead and grab a servo. We'll toss it into channel 1 for the ailerons. And that's our connection. That's everything we need. I've got my power source here. It's routed around the back to keep it out of the way. Well, we've got a servo connected to the servo manager. If I wanted to hang additional servos, I could. It wouldn't be a problem at all. In fact, you know, grab another servo here, and we can run this off of channel 2, which will be elevator. And there I have 2 servos connected. The ideal, you know, application, again, I can run a Y adapter off of here and run, you know, if I've got 2 or 4 aileron servos, I can run that off of, you know, my channel 1 output. And ideally, you want to try to distribute that as much as possible. So I may run two aileron servos on the right side, 2 aileron servos on the left side, and do a Y adapter on each one of those channel outputs. But the neat thing is the servo manager is going to intercept all of this. So let's go ahead and power up the transmitter. Tell it to transmit. And we'll power up our system. And there we go. Okay, we're getting 7.6 volts in from the battery, so we're good there. And we're going to go ahead and go into, if you know, the easiest way to get in is hit your airplane, go to System, and go to Sensor. And now you're looking at all the different sensors that are available from the HTSS Advance. Remember, the Aurora 9 is going to reflect whatever sensor station is connected to it in terms of what options are available regarding you know, the display. So if we go into Easy View, or Servo Manager, we'll go do that first. So this one is specifically for the Servo Manager. Servo Manager, you know, 1, 2, 3, and 4, those are 4 ports we see coming out of the HTSSM. We can rename that. So say SV1, we'll go ahead and call that we'll call that aileron 1, and enter that. So now we got aileron 1. We could do aileron 2, whatever we wanted to down through the list. So say this is our aileron 1. It's going to show the max current for the one you have selected. So I can go through and select the different servo output ports, and it's going to reflect whatever the max current is and the current consumption as well. So say for example we're on aileron 1. Let's go ahead and get this servo active a little bit. And we'll see it's already chewing up about 2.5 amps there. There's 3.9, 4.4. And keep in mind, this is on 7.4 volt too. If we drop down to 6 volt, which the servo is certainly rated for, you know, your current consumption is going to increase beyond that. So now all of a sudden you realize I've got a you know, real nice high voltage, high torque servo here, and you know, I spent good money on it, and it's certainly enough to handle my plane. But then all of a sudden you realize at 4.4 amps, multiply that out by, you know, 4 or 6 or even 8 servos, we've got a lot. You know, we can chew up that 30 amps really quickly. Now it's bursty, so the chance of you moving all control surfaces in the same fashion at the same time are pretty slim. But you have the potential of consuming up to, in this case, you know, 4+ amps off of this one servo. So you want to make sure your budgeting is on the money for whatever your application is. But the Servo Manager allows you to take a look at that. Now we can go through and look at the Easy View version of this, and you can always reset that max if I wanted to reset it and retest it as well. We'll go ahead and take a look at the Servo Manager or the Easy View version of this. Easy View is going to walk down through all the different screens that the HTSS Advanced sensor capabilities are going to give you. So we're on screen 5 of 9. If we go back through here and start off with the first screen, there's our speed and altitude, airspeed and variometer. So realize speed would be GPS speed, airspeed, and then variometer. Now you can go into further settings, and we'll talk about that in part 3 of the whole video series about how you can determine what does your actual sensing. voltage and current, wattage, and an RPM, sensor 1 and 2, aileron 1. So now we're getting into our servo manager. This is the one we set as aileron 1. So this is another view of, if you just touch that, it resets it, touch the max. This is another view in real time of our servo consuming power. And again, we got a 3.7 amp there. And what you'll find too is, it's kind of interesting as you experiment on the bench, as far as actual max consumption, you think just stalling out a servo, putting a lot of torque in the servo would immediately max it out. But if you're moving it slow, since this is these are digital servos, so it's sending a pulse to the motor, it's actually pretty darn efficient when it comes to loading. It's fast movement that really chews up that amperage. So you can work it through very slowly, even to stall, or nearly to stall, and it doesn't really chew the amperage up that bad. Start moving your high speed, and suddenly you see your peaks going up. So that's the servo manager. There is a data port on the servo manager itself, so you can update the firmware separately. You do not need to connect the data port into the HTSS Advance. You're going to use the included cable, the hardwired cable, into the M1, M2, or M3 ports, and then connect your servos out the left side, and then the hardwired servo leads are going to go into whatever channels you actually want to monitor. You don't have to monitor all. You can certainly connect servos directly to any of those ports off the receiver. It doesn't interrupt any receiver function at all. It just gives you the ability to jump in line with whatever servos you're feeding, and then assess the current consumption and the performance of each of the channels. The HTS AS airspeed indicator is a simple air pressure airspeed indicator. It utilizes a pitot tube to pick up incoming air currents on the front of the aircraft, and then also comes with some silicone tubing to connect the small brass tube, little function as your pitot tube, back to the sensor itself. Installation is really simple anywhere within the aircraft. Again, it's very interference resistant, so it's not a problem. You're just going to want to space it out to where you've got enough tubing to work with to get to your pitot tube exit point all the way back to your sensor. And testing of the unit is pretty simple. As far as installation practices, keep in mind you want to make sure that when you put your pitot tube in, of course it's free of any obstructions at all. After you've done the installation, make sure that it's clean. If you're sticking it through like a foam aircraft, the nose of a foam aircraft would be a good location. Or you want to be about 4 to 6 inches away from the root of the wing and on the leading edge. The goal being is you're out of the prop wash or any sort of air interruption or disturbance in the air coming in. You want as clean an airstream as possible to get the best accuracy off your pitot tube. And you're going to want to place it, again, forward facing. The key being is that as your aircraft's flying and you look at the incident or the pitch angle of the aircraft in normal flight, you want to make this as parallel to that pitch angle as possible. So when you're in a normal forward flight, you're getting a direct impact of the oncoming wind into the forcing air into the end of the pitot tube. And setting it up is really easy, or connecting it's really simple. You just have the sensor itself, the HTS sensor, and you're going to plug in. This is only compatible with the HTS SS Advanced sensor station. And we talked about the M1, M2, and M3 for the servo manager, which the servo manager plugs into one of those ports. These are like the universal ports for the newest sensors. You plug in the airspeed sensor into one of the M ports, and if you're using a servo manager, you can plug it in one of the M ports. It really doesn't matter. The unit's going to detect which sensor is connected to it, and the interface will reflect that information accordingly. So we're just going to go ahead and plug this right into M1. And then, of course, our system's already powered up. Normally, we want to have all our connections done, but it'll work just fine this way. To bring up the display on the Aurora 9, you're going to go ahead and go into your aircraft menu, System and Sensor. A couple different ways to view it. You can go into the cockpit view or the easy view. The cockpit view is going to show 2 pages, the first one being airspeed. Now, what you're going to want to do before you do that is go into Advanced, and you're going to want to choose that you're using your speed as the airspeed sensor, not GPS and air. You can do GPS and air. Will blend the two of them together, or you can choose just air or just GPS. In this case, we're using the airspeed sensor, so we want to use just air. And once you've had that set, then when you go into your cockpit view, it's going to reflect the airspeed indicator, is going to reflect the readings taken off the HTS AS airspeed sensor. So testing it again in the bench is really simple. All you do is plug in your tubing and apply a little bit of air pressure to it, and that'll simulate as if the aircraft's going through the air. And it really doesn't take a whole lot. I'll go ahead and apply a little bit of pressure. and you see it immediately reflects that pressure coming in as forward airspeed. Now the other view that we've got is the Easy View. Easy View has several pages to it as well. It shows we're on page 2 of 9. Just tap through that and you'll see all the different pages that you can view. The nice thing about this is it gives you a bigger display, so when you're flying you can actually glance down to see your airspeed indication. It does hold max, so if you're doing a test run on a flight and you want to see what your maximum airspeed was, it's going to retain that after every section, actually until you reset that. So just tapping the max will reset that to 0 before you take off, and then go ahead and go through your flight. And you see it'll register as much pressure is oncoming, it'll register that max speed again and hold it, and then back down to 0 since I released the pressure. And that's it. HTSAS is very simple to install. You make a couple changes on your Aurora 9 display, and you'll be able to see that reflected real time in your cockpit view or in the Easy View as well while you're flying. Connecting the sensor stations to your optimal receiver or your telemetry capable receiver is really simple. In fact, the nice thing is there's not a lot of setup you have to do or anything to tell the telemetry enabled transmitter like the Aurora 9, or you've got the Optic 6 Sport 2.4 gig here, or the Eclipse 7, or any of the Hitec telemetry capable radio systems. It's all built in, so all you have to worry about is the physical connections, and then once you power on the system, it'll register or realize that you do have telemetry connected to the receiver, and all the sensor views will become available to you for that sensor station. So starting off, we'll use this Optimus 7 as an example. This is a 7-channel receiver, and it has the data port, which is the data port we're going to use, and that's pretty much it on the receiver itself. And then on the sensor station, we have both the HTSS Advanced and the HTSS for Nitro. We have our blue installed on a plane for demonstration, so we won't use that on the bench here, but the connections are absolutely identical. In either case, you have a power port, and those are indicated just by the letter P. And it's a full-size radio connection. You see it right there on both of the sensor stations. And the sensor stations ship with a female-to-female connection, which typically, if you look at an extension, it's going to be male to female. This is a female to female. So we're going to pay attention to our polarity. Now these are keyed, but if you're ever curious on a radio connection, whenever you see a notch, that's going to be the data channel. So just look to the farthest pin away and know that that's your negative. So if you have a non-keyed connector that you're putting in, it's an easy way to keep track. And it's the same for all the servo connections and everything else. The key indicates the data, so always go to the farthest away from it, and that's your negative. Easy way to remember it either way. So in this case, it's keyed. We'll go ahead and plug in our radio connection. And now this is power. All this is looking for is radio power. So for example, we're going to go ahead and use, in this case, just a life battery. It makes it simple because it's big capacity for me to do these demonstrations, so I don't have to worry about it running down too quickly. We're going to power on our receiver, just like we normally would. In this case, we've got a couple radio connections coming off the battery, which makes it kind of handy. And we can go into either the battery port, or we can go into any of the servo ports. Something to keep in mind is on a radio system, this is a common bus. So if you've got negative on the farthest pin, the center pin is positive, that bus, as soon as you plug in any of those ports, it powers all of the other connections. So that's why you can sometimes slave devices off of unused ports and still get power from them. It's not a problem at all. So we're just going to go ahead and tap into the channel 1 port here. Again, negative being furthest away. This is a non-keyed connection. So the only way I can really tell which way my polarity is to know that farthest away from the key is my negative, so I'll plug it in accordingly. And that's going to power on my receiver. And when I plug in and I'll just do this so you can see what happens. All I can do is on the power input on any of the sensor stations, I can plug into any of the available ports. I can even plug into the battery port if I want to. So in this case, I'll go ahead and plug into the battery port, and it's keyed, so I know which way to plug it in. And you'll see immediately on this HTSS Advanced, the blue LED starts flashing very rapidly. Now this is what takes place through all different states. That rapid flashing shows that it is powered up. It doesn't mean anything else other than just it's receiving power. Your sensor station is also going to come with another cable. One is a very small connector, a micro connector for the sensor station data port, and the other is a standard radio connection. Now this is going to plug into the data output on your optimal receiver, or your telemetry capable receiver. And we see the data port right there, so I'm going to go ahead and plug in. Again, negative furthest away from the key. And then I'll plug in the data into the data port. It's just marked D. On all of the sensor stations, you'll see one port marked D, delta D. It's for data. And I'll plug in my, my data connection there. And that's it. That's all it takes to connect a sensor station to your Optima telemetry enabled receiver. And then we can just start plugging in our sensors, and we'll do one quick one for example. We'll power on our Aurora 9. And it's registering incoming voltage, so it always tells us on the Aurora 9 we've got 6.7 volts coming in, or whatever our input voltage is from our receiver pack. And then we've got 77% of our actual transmitter pack showing. So right now, if I go into my, since I'm on the advanced, if I go into my model, system, and sensor, it's going to give us all of the things that are capable for that sensor station. So it's important to remember when you're using like the Aurora 9, the sensor view is going to display all the sensors that that particular sensor station can show. So for example, if I power down and unplug my receiver and I switch over to the nitro station, you're going to see a different suite of sensors being made available. And again, all these connections are the same for all the different sensor stations. So now when I power back up, power on my transmitter, and power on my receiver. Okay, now I go into my model menu, go into system and sensor. Now I've got a different suite of sensors being displayed. So I lost like the servo manager, the variometer, I lost the airspeed indicator. I do have airspeed with GPS. I have ground speed with GPS, but there's actually a separate airspeed sensor, of course, that the HTSS Advanced can receive, but that's not an option on the Nitro. So these are just the Nitro options. And then, of course, from there you can go into the individual sensors information. We don't have any sensors plugged in. Let's say we went into temp here with the system powered on. I can go ahead and grab one of the temp sensors, and I can plug it into one of the temp ports, and it'll immediately recognize right there positive 71 degrees Fahrenheit. So, and the sensor is working. So it's real flexible. It's not cantankerous about the order in which you do this procedure. There are some sensors that require certain order operations, for example, the fuel sensor. But generally speaking, it's a very flexible and dynamic connection to the sensor station. It's just a couple of wires, the data port and the power, and now you're ready to go to start plugging all the different appropriate sensors into your sensor station. As far as mounting goes, like anything else, you want to keep radio components as far away from power components as possible. So you don't want to put your sensor station and all the leads close to, high current wires going to your main flight pack that are being drawn at high amperage rates. It's shown to be very resistant to any kind of interference or any sort of problems, but you always want to be mindful of that and keep things separate as possible. Otherwise, it's extremely flexible and simple to get your sensor station plugged in to your Optima receiver and ready for telemetry data. Well, now that we learned how to connect all the sensors to the sensor stations, make sure you come back for part 3 where we talk about how to get that data back and what we can do with it, including the supported radio systems as well as the add-on modules and interfaces. For more information, visit hitecrcd.com where you can see all the telemetry options available, supported documentation, firmware upgrades, and everything else related to the Hitec Telemetry system.